Okay, so today we're going to solve examples to get more familiar with how the magnetic fields surround specific current elements, whether they are straight current elements, whether they are looped. And what I will do before I go to example one, I would like to remind you exactly to follow up on the discussion with your colleague. So here, I'm going to add one page. Okay. And I would like here to remind you on the following. So this is a reminder. What we've learned so far is that there is, when we have an electric current like this, and let's assume that this is infinite long. So because it's infinite long, it's going to extend beyond that point. It's just that we, and then we said that the current is going to close somewhere. All right, so it's not like a section, it's not, the current is not like the charge where it can stay at one point. The current has to flow, and the current has to flow on closed paths. So even if we show a straight line, at some point this line connects with itself. All right, in that particular case, it's somewhere very far away. And also we said last time, then when we talk about current filaments, or what I mean by that, it's a word we use for very, very thin currents, all right? So we indicate them either like this or equivalently like that, because we reserve the symbol J for densities, usually. This is a symbol for densities, for current densities. This is a symbol for current, total current. However, when the current flows in a filament, like in a very, very thin, on a very, very thin line, is all concentrated into one point. So even if densities apply to one point, in this particular case, that's the only point where current flows through. And therefore, in current filaments, I, which is a total current, is equivalent to a J. I mean, sometimes you will see it like J, sometimes you will see it like current. All right. So in this case, whenever we have a current filament, we will always use an I, because we consider it's like the point charge. A current filament is equivalent or the dual to a point charge. You remember, we had point charges, we had charge densities. A charge density is a charge at one point when there is a charge distribution on a surface or in a volume. A current filament is equivalent to a current density if the current is distributed, all right? If the current is all going through one point. So we use total current if the current goes through one point for a current filament, and that is equivalent to density. But density is reserved for currents when there is a current distribution, all right? So then we differentiate between a current density and then a total current, because the current is distributed. But when the current goes through one line, the density and the total current primarily are the same thing. Okay, just in case when you read, you see them used interchangeably. So now the next thing, after we clarified that, because I know that some students had a question about this, Now let's try to find the magnetic field from this current. The magnetic field, how do we find it? From the right-hand rule. So from right-hand rule. What is the right-hand rule telling us? It's telling us that when you have a current that flows along the direction of your thumb, all right, of your right hand, the magnetic field is circling this current along the direction of the other fingers. So in this particular case, if you use the right hand rule, what you're going to find out is that the magnetic field goes like this, all right, around it. And then it starts like this. It goes around it in closed paths. And how does it go around it? Like this direction. And those extend, all right? So the closer you go to the current, the stronger it gets. You will never use the formulas on the current because all of the formulas we're using on the current, they go to infinity and it does not make sense, all right? So you use the formulas we find for this magnetic field everywhere, but not on the current, just everywhere else. Okay. So now what do? We try to do the next thing to do, and that's now I'm coming to the discussion with your colleague. Let's assume that we have two of these currents. So I'll take two that are along the same direction. Okay, here. And then a similar one. And let's try to find the two magnetic fields. So from one, the magnetic field looks like this. And from the other one, looks like this. Let me see. Okay. So what happens here, so if I were to show the two currents like on their plane, so I will then look on the plane of the two currents. Let's assume that this is the XY plane. The XY plane. If I show the two currents on the XY plane, how are they going to look? I will take this one. But what I'm going to do here, I'm going to, since I am on the XY plane, I'm not in 3D anymore. I will remove this. And how I'm going to show the two currents is the following. I'm going to show here. And then here. That's from one. And then from the other will be like this. All right, so what happens in between the currents? What happens to the two magnetic fields? How do they interact with each other?
Wouldn't they cancel each other out?
Exactly. So here the fields cancel out. And if I were to take bigger lines around the current, so for the current to the left, if I take, say, this one line, oh, excuse me. If I take this one, then I will find this here to go like this. Okay, look at this, how the blue lines go outside of the currents. And if I take, what did I do? And if I take bigger green lines, bigger green loops, rather, I would like to say, because we're talking about loops in the magnetic field. If I were to take a bigger green loop, say, take this one here, how is it going to look out there? So what happens outside of the two currents?
They should sum up and
Sum up.
create
Yes, they sum up. Exactly. Okay. Now, if I were to take the same thing and then use two currents like this, like that. All right, one is up, up as before, but the other one is down. You expect, without going in the same detail in between the currents, all right, you expect, I mean, in drawing the magnetic fields, you expect that the opposite is going to happen. That here, the magnetic fields will sum up. So here, the magnetic fields will remain the same. For this current. But here, the magnetic fields for the other current will reverse. And if I take longer, I mean, larger loops, and then it's going to be extended beyond for the green, and for the blue, which is for the current to the left, for then the blue is going to look like this. All right, so what happens with these ones? They sum up here in the center. And they cancel out here. And why is that important? This is important because we use this to create transmission lines. So you will always see in transmission lines, you need to remember that when you see in the future, after next week, you will see that we talk about transmission lines. Our transmission lines will always have two wires. One wire is going to have this current and the other wire is going to have this opposite current. And why we do that? Because we want the magnetic fields to be strong here. All right. And in this particular case, all of these fields will be strong here. So we confine practically the fields by having opposite currents. All right. Any questions on this? I think now we'll be ready to solve this problem. So practically what I do here is to show two loops instead of two straight wires. I'm showing two loops. And in this particular example, I would like to find the field in the center, between the two loops. And we have that, so in the book, in the section of the book, which I believe I have already included in on Canvas, but it's chapter, let me tell you, 7. And in your book, in example 7.3, which is, read all of these examples from the book, are very useful, very similar to what we do. In example 7.3, they solve the loop problem, which in fact you had also in your homework 4. But there was, the solution is already in the books. It's page, no, it was not a homework 4, excuse me. The homework 4 was another one, was in the chart. I'm sorry, I apologize. Also that solved in the book, but this one is on page 306 and it's in chapter 7, and it has the loop problem. All right, it has which we solved last time. We found, and in fact, I will write it here the way it is, because we're not gonna try to rederive it every time we have a loop problem. We need to remember the formula that from a loop, so let me write it here. If we have the loop C1, the magnetic field at point A from loop C1 is given by, so CH1, and in fact is, you will see it in the solution later, but H1 at that point A for Z equals, assuming, all right, for point A, let me just write because I don't even show Z here. So at point A, is equal, is of course along the Z direction, and is equal to the current times the radius squared divided by 2, and then you have A squared plus H squared, where H is the distance, is O1A, and let me, yeah, H2 squared in this, excuse me, H over 2 squared in this case, because it's at a distance H over 2, and that's 3 over 2 to the third, to 1.5 power. Okay, the same thing with H2. All right, so practically we will see that later. It's in the book, and we derived it last time. All right, so the first thing to do is to identify the magnetic fields from the two loops. I have here also the solution. The magnetic fields from the two loops, if the two loops are far away, what you see are, you take each one of them, the top one, and you see how the magnetic field lines go through the loop. All right, so on the surface of the loop, just what happens on the surface of the loop, which is this one. On the surface of the loop, all the magnetic field lines align, and they are perpendicular to the surface of the loop. All right, the same thing applies to the second loop. But as you move away from the loop, the lines curve, because these lines have to close somewhere, and they will close because they make all of these lines. Each one of these lines has to close on itself. So each one of these lines makes a loop itself. But this is how they look when they are at a relatively large distance compared to the radius. And the magnetic fields then, if you want to write the magnetic fields somewhere along the z direction on the z-axis, in this particular case, the z-axis was here, all right? Then you write the two magnetic fields from one, from the other. You pay attention to the direction of the two fields. You will never sum up anything which is a vector without knowing the direction. And in this particular case, what you see as a first indicator is that along the z-axis here, the magnetic fields align because of the direction of the currents. The currents are here. All right, they go in the same direction. And so along the z-axis, the two magnetic fields align and they sum up. Now, what happens if I bring the loops very close to each other? They don't touch, no, but they are very close. What happens to the two loops? Practically, because the loops are identical, they are as if they are one loop, but with twice the value of the current. Okay? It's not like two separate loops. They look as if they are one loop, but twice the value of the current. Because they are so close and the magnetic fields are equal for each one of them, and they align perfectly and they sum up. So the total magnetic field will be twice the value of the magnetic field that is produced by each loop. Why is that important, you may ask? This is a very important thing to remember because a coil, let me draw a coil now for you. Oops, no. I will draw a coil in three directions. Okay. All right, let me do this differently. That looks like a spiral. It's not a coil. So, okay, let me do it in an opposite direction, like this, and like this. Okay, and I will do this to the ones which are at the back. So these ones are like this. All right, and the other side of the coil. And practically a lot of times in the coils, they put them around a bar that looks like this, just to hold them in a position, all right? Or you can say it's like that, the bar. All right. So what happens here? If you see, you have four loops. Number 1, 2, 3, and 4. And each one of them has the same current because it's part of the same loop. All right, but they wind around this bar. And so what you see here in terms of current is like the current, if it flows here, it will go here. It will come around here, 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 and then it's going to go out. So practically, it's like you have 4 loops, not 2, that we had before, but for loops where the current that flows is identical, all right? Assuming that you don't have any losses. So what happens in a coil like this? The magnetic field is 4 times at the center of this coil at the center of this coil, the magnetic field H is 4 times the magnetic field of its loop. And that's extremely important to keep in mind. Why is that important? We use this. Why do we use these structures? How do we call these structures when we use them? You have seen this figure in circuits. How do we call this?
A solenoid, inductor.
Solenoid or inductor, right? Usually in circuits, we show an inductor like this. Why do we show inductors like that in circuits? And we show capacitors like this, symbolically. Why? Because that's how we make them. It's a symbolic representation, but what the symbolic representation is telling us is exactly that we make capacitors from parallel plates that are at some distance with the dielectric, and we make inductors by creating multiple loops. Now, of course, we are very creative on how those loops are created. So, for example, we will see later different examples. I don't want to go off our subject right now. Okay, but so you see why the example, this one was very important. What would happen if the two coils had opposite currents? Let's say, what if, question here, what if the coils C1, C2, the two loops rather at this point, had opposite currents, I. So instead of flowing like this, they would flow, how? The purple one would go like this, and the green one would go the opposite direction. What would happen to the total field inside, you think? What if I were to take the two coils like that? Okay, so the purple one is like this. It comes out here. This is a coil, cross section of the loop. All right. This is the purple, and the green one is this one. It goes like this and comes out here. All right. I've changed you see here, I've changed the directions of the current. So I can take that here practically. All right, so assume that this is the cross section of one coil, of one loop, and that is of the other. How would the fields look like? The field from the purple, let me do it purple too, is going to be, the magnetic field here is going to be all along this direction. All right, from the right-hand rule. And let me see. Yeah, and then how would the green be? would be the opposite direction. So what would happen if my two coils had here separate opposite directions in the currents? How much would be the field inside and the field outside?
0, right?
0 inside, exactly. The field inside would have been 0, and outside here, look at this one, it would have been practically outside. It would close accordingly to the loop, so it would be strengthened outside. All right, but
Would be
inside,
double.
not exactly. Would not that it will be stronger outside than inside, obviously. But yeah, do double, but not double, not compared to the inside. The inside is going to go to 0. All right, but it's going to be, it's going to be the sum here 0, and outside will be the sum of the two fields. So the opposite of what happens here. And so if you were to have two loops with different directions in the current, then inside the two loops you will have 0 field. One loop will cancel the other. And that's why we only bring opposite currents next to each other only if we want to cancel the fields, like these currents. All right, we only bring them close to each other in the loops if we want to cancel the fields inside the loop with opposite directions. If we want to strengthen the field inside the loops, and we have multiple loops, and we bring them together, we make sure that the current direction is the same. Okay? Any questions? So my advice will be, in this particular case, look at this, because don't get confused about what happens in between these two currents where they're opposite, and in between these two currents, the fields sum up, and between two loops with current directions where the opposite happens in between, in the area of the loop. Do you see what I'm saying? So you have in the straight wires, practically, unless you have one wire on top of the other, all right, where practically the field in there, you don't care. I mean, it's very strong, but it's confined, totally confined, if you bring two wires very close to each other. But in loops, so to confine the field between two straight wires, the direction has to be opposite. But in a loop, when you have two loops, to confine the field on the aperture of the loop, you have to bring the two loops, like you see here, with the same direction in the current. And it's on the basis of those things that we create a solenoid like this, which is practically an inductor, or where, as I said, we use this idea to develop transmission lines. All right, so just make sure that the straight wires from the loops that are aligned, they give you different, I mean, the direction of the currents has to be different to be able to get the largest field in between them. All right, so look at this example and look at this example here carefully. All right, to be able to understand what is going on. In fact, here, to do it more carefully, so you remember when you see that, let me do it, I will erase it for a moment, just so when you go back to read it, because this is important, I would like you to remember this for the midterm. All right, so what I will do here, show you is the following. Let's assume that here we have, I will do it more carefully. Okay, here. And here we have the lines like this. On this one. And here the lines, they will go out, obviously. All right, but on the other one is gonna be this, and they will go out like that. And so practically in here, so you're gonna have the field is gonna cancel out. And out here, because this one, well, of course, they are very far away. But when this comes here, it's gonna be like that. The magnetic, excuse me, the purple. And of course, magnetic field. And when this one comes here, they're gonna cancel out as well. It's gonna be like this. But from the other side, from the other piece of wire, anyways, remember that when you bring them here with the same, with the opposite direction of the currents, they cancel out and practically primarily cancel out everywhere in this particular case. But of course, it's going to be very close, much closer to zero at the center here. Then it's going to be somewhere outside because of the relative dimensions. So they cancel out in these two. Okay. So now there is, and do you have any other questions before I introduce talk about the total magnetic flux? Okay, I don't hear anything. So the total magnetic flux, when you have a loop, and we have talked so far about the magnetic field, all right, and the magnetic flux density. But if I am in a loop, and in fact, it might not necessarily be a loop with a current, but what I do, let's assume that I have a magnetic field that has been somehow excited by a current source somewhere. And I see this magnetic field here. And then I define an area S. So I define it. And in this area S has also a direction. You remember we said every surface has a direction. And in this particular case, because I defined the surface to be like a plane, but to be like a closed, of course, a surface, not a closed surface, it's a surface on a plane. It looks like now I have defined it as practically being the area of a circle or an ellipse or something, whatever, it's a surface. Then I call the total magnetic flux psi, and a lot of times you may see it as phi, other people, all right? They use either one, it does not matter. From, I think the book is using psi, if I remember, let me see. At some point, I don't want to use it. Yeah, the book uses this symbol. All right, so we're gonna, but you may see it as phi somewhere else if you are looking for a magnetic flux. Then this magnetic flux is the integral of B dot inner product with the surface on that surface. That is called the total magnetic flux. And why is this important? compared to, now, because next time we are going to introduce the concept on Friday of the inductance. So for example, if the magnetic field B was coming from a loop, as we said before, from one of the previous loops, if I find the area of the loop and integrate over that area of B, like assume that this loop had a current, and then I would find the total magnetic flux through the loop that generates the magnetic field. Then if I were to divide that magnetic flux with the current, that would give me an inductance. We'll see it next time. That's why it is important to know how to find the total magnetic flux, but we're going to do examples next time. So that's what we covered today. And remember these formulas. Read the example in the book because it has a very detailed solution of this problem. And we did it last time, obviously. I'm not skipping the derivation. We did it last time, but I would not like you to remember how to rederive it. I want you to understand how the derivation was done and remember the formula. So today we're going to start solving problems as a review for the midterm, and I will record this session. Now, I wanted one thing to people. There was a couple of students who said that it's more important to them to put the recordings immediately as opposed to do editing and so forth. And I have to tell you the following. I do the report, the videos I'm creating is not that they're not created by the university, like they normally does in classrooms. I create these videos and I put them on YouTube so you can access them easily instead of loading them on, and it takes even 3 times longer to be loaded on Canvas. But if I were to do this, then I have to edit them because I'm not supposed in these videos to have any of the students and their names show up. So if I were not to edit them, then I would have to ask a permission from each student to be highlighted during that video that is public. And that would take me weeks to do this. That's why I edit all of these discussions with students. I have to remove, unless somebody's asking me through, and then it does not necessarily show because I share my screen. That's why I cannot just do it. I apologize, I cannot do it immediately. That's the bottom line. I have to edit the videos before I post them. So, however, I put my notes, and then also you need to remember one thing. This class is not asynchronous class. It's not asynchronous. In an asynchronous class, it implies that I would have to put everything to record it ahead of time and put it there and then you can take it anytime you wish. This is not an asynchronous class. So I have to take it and then place it, and the class is at a particular time. So in any case, I just asked for clarification why I have to do the editing, just for some students who complained that the videos are not immediately there. So in any case, I just want to clarify it. So I try to do my best, I can, to deal with all of this material that I put on the web. Any other questions you may have before we go? We're not going to have an exercise today. So we're going to skip the exercise and have a quiz on Friday.
What was the page number of the textbook?
The page was, 1 second, 306. It's chapter 7.
Thank you so much.
You're welcome. Okay, any other questions?
Professor.
Yes.
How long until how long after the problem solving sessions the videos get posted?
Okay, I will I'll tell you, probably I will do it the next day.
Okay.
Because by the time we finish the classes, say 6:30, by the time I wait until the video is processed on my laptop, it takes about maybe 15 to 20 minutes. And then I have to go home, and either I can do it, then I have to download it, then I have to process it. So it's going to be the next day.
Okay. Gotcha.
Okay,
Thank you.
Sure. All right. So I will see those of you who can come this evening, or otherwise on Friday, excuse me. Okay, take care.